This is NP Chen and welcome to my mathematics class. Today we will learn some standard results on limits, and thereafter we will discuss the limit of algebraic functions. In my last class I have solved some questions of limits based on algebraic functions. Today also I will discuss the limits of algebraic functions after discussing some standard results on limits. Okay, here we go. Some standard results on limits. First one, limit of alpha as x tends to c is equal to alpha, where alpha is a fixed real number. Okay, so alpha limits, for example, let me explain this one. For this, if we have a limit of 2, c is a constant, c is a fixed real number. If c is a fixed real number, if we have to find out the limit of 2 as x tends to any okay constant, let's suppose 1, you will have to limit of 5 as x tends to 2, also 5. From here you can say limit of constant as x tends to any constant is the first one constant here, right? Limit of alpha as x tends to c is equal to alpha, where alpha is a fixed real number. So limit of constant is constant as x tends to any constant. It doesn't matter whatever it may be. All right, uh, clear? Next one. Let's move into next. Second, limit of x raised to power n as x tends to c is equal to c raised to power n. It works for all n belongs to capital N. Capital N means set of natural number. What does this mean? Set of natural number. This one is set of natural number and represents here the set of natural numbers. Okay. To explain this, here I can take for this, uh, if example limit x tends to any, okay, limit of x raised to power 2 or x tends to 2, we can write down 2 raised to power 2 according to this is equal to 4. 4 will be the limit of function. Okay, limit of function according to this standard results. Now clear? So let's move into the standard result of thought. Limit of function f of x as x tends to c is equal to f of c. Very interesting, where f of x is a real polynomial in x. As I told you in the first video of calculus, I mean to just introduction to limits, where I explained meaning of x tends to a and also the limit of function. In that video I explained about that also. So okay, here limit of f of x as x tends to c is equal to, you can write down the f of c, where f of x is a real polynomial in x. Here let me take for this example a limit here x square plus 2x plus 1 as x tends to 1. Simple example I have taken here. You can see, just I have kept in a closed loop. Alright, here lack of a space also. Okay, it doesn't matter. So important thing, you should understand this. If it's not clear, you can comment in the box. Limit of x square plus 2x plus 1 as x tends to 1. What will be the limit of this function according to this? So we can apply here, see very clearly. According to this, limit of function f of x as x tends to c is equal to f of c, where f of x is a real polynomial in x. F of x is a polynomial. Here x square plus 2x plus 1 is a polynomial. What is the definition of polynomial? Again, it may be in confusion if you don't know the polynomial. So polynomial, what is the polynomial? uh, means expression in this form. You can just in a simple way, let me here a 0 x raised to power n plus a1 x raised to power n minus 1 plus dot 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 plus a n. This expression is called your polynomial if powers of variable, right, are non-negative integer. If okay, n comma n minus 1 comma and so on are non-negative integers, if these are okay non-negative integer, so powers of the variable should be non-negative integers. Non-negative integers means you can take 0, the power of the variable may be 0 or positive means natural number, you can say the or positive integers. Here n is a positive integer or non-negative integer, 0 or positive integers. No, so that you can say okay n minus 1 and so on. Okay, these are the non-negative integers, and a not or you can say a 0, a 1, and these are the coefficients of the variables. All right, here coefficients, and the final term you can say the constant of the polynomial. All right. So I think okay polynomial is clear. If I write like this way x raised to power, and let's suppose another example which is not polynomial, it will be easy to you to understand. X square minus 2 plus 1 upon x plus 3. If you say, is it polynomial? No, this is not in any way polynomial. Why this is not polynomial? Because here power of this is not a non-negative integer, and power of this is also not negative. 1 upon x means ultimately you can write on x minus 2 plus x raised to power minus 1 and plus 3. Here non-negative integer, here non-negative integer, right? This is not a polynomial. Okay, this is not a polynomial. And so another example I may take, okay, which is not polynomial. Here I am writing lack of space. Here if I write okay root x 2 root x plus 3x, this is also not a polynomial. Polynomial. Why this is not polynomial? Here also power of this variable rational. According to the polynomial, we need non-negative integers. And okay, so that's why this is not polynomial. If we have a polynomial, then then we can write down okay according to this result we can write down the 1 just f of c means f of 1 here is equal to f of 1. We can write down if we suppose this is a f of x, and it's gonna be 1 square plus 2 into 1 plus 1, and here 1 plus 2 plus 1 is gonna be 4. So 4 is limit of this function. Okay, and similarly we can use this standard result if you have a limit of absolute value of x, or absolute, this is called okay absolute value function. If okay your variable are in terms, if variables are inside the modular sign, that is called your okay absolute value function. This is the absolute value function, and here limit of absolute value function as x tends to c is equal to mod of c, simply, right? These are the first four results, and let's move into the algebra of limits. Okay, already I have a tool. If you go through that video, you can also find out, right? Okay, so again I've added, okay, it will be easy to you to understand the questions which we are going to find out. Okay, so let f and g be the two functions such that limit of f of x as x tends to cl, and limit of g of x as x tends to c is equal to m. This is the sign also for limit. For limit we can write down in these two form. Either form you can use, just like limit. This is also a limit. This also a limit, and or you may use okay this also symbol limit. Okay, anyone you can use, it doesn't matter. Okay, then these are the algebra of limits. Okay, algebra for limits. If we have alpha into limit of alpha f of x as x tends to c, then we can write the alpha limit of f of x as x tends to c. We can say here coefficient coefficient we can write down outside, or a coefficient you can say, or you can say okay any scalar, non-zero scalar, if isn't product with the function, we can write down here outside, right, of the limit of function. Okay, so like this way we can write down. It works for all alpha belongs to real number. R, what is the R? R means the year. Okay, set of real numbers. Set of real numbers. R means set of real numbers, and means okay set of natural numbers. Set of natural numbers. So many circles. I have so many circular diagrams I've made, and inside I've written. Okay, it's alright. You can understand. I'm explaining. For all alpha belongs to R. R means set of real numbers. Your alpha may be any real number between minus infinity to infinity, except we can say the zero. If there is a zero, then it's gonna be a zero totally, and limit of zero is a zero. Okay, all right. And here, if we have a plus minus, we can write on this separately, as here I have written. Okay, this also all right. Already I have discussed. Okay, this also, if they are in product, then we can write on this separately, right? Separately, and then separately we can find out the limit of these functions, and then we can multiply, right? Okay. So done, and this is also clear. Provided m is not equal to 0, provided limit of gx as x tends to c is not equal to 0. Alright, you know, right? If denominator is 0, then value is undefined. Okay, and this means okay, limit will not exist. That's why we need here denominator not equal to limit of the denominator should not be equal to 0. And here, if we have this one limit of 1 upon f of x as x tends to c, we can write down 1 upon limit of f of x as x tends to c is equal to 1 upon it. So simple. Okay, if we use okay this one fourth one property, we write the limit of 1 into limit of this. Okay, limit of 1 is 1, because according to this, limit of alpha as x tends to c means alpha. Limit of 1, so it's understood thing, so that's why we don't write down, and directly we find out the limit of this one. So you can write down also in this way, right? 1 upon L. No need to write down separately limit of this, limit of this. Okay, provided L is not equal to 0. The sixth property of algebra limits, here, limit of f of x raised to power n as x tends to c, we can write down okay, limit of f of x as x tends to c whole raised to power n is equal to L raised to power n, and for all n belongs to n, and it works for all natural numbers, because n belongs to n means set of a natural numbers. Alright, I think you all understood how these standard results work, and how these algebra limits work in calculating the limit of function of algebraic, right? Algebraic functions or algebraic functions, and these property also work for other non-algebraic functions also. All right, so let's see. Okay, others also. Now let's discuss sandwich theorem or squeeze principle. Mm, I've just written sandwich theorem or squeeze principle, and then some more standard results on limits I've written, and one more important theorem on limits we'll discuss. Okay, let's say sandwich theorem or squeeze principle. What is the statement of the sandwich theorem? If f, g, and h are the functions such that, in this condition, if f, g, and h are the functions, f of x less than or equal to g of x less than or equal to h of x, right? They are in this order. For all x in some neighborhood of c, some neighborhood of c, except possibly at x is equal to c. Here, okay, for all x in some neighborhood of c, either okay, right? Just they may approach from the left of C or right of C, but they are not at x is equal to c. Neighborhood of c, suppose okay here, if I write here x and this okay here, c minus delta, let's suppose, and c plus delta. Delta is any positive number, uh, uh, very small positive number, whatever you may choose, as much small as you can. Then here okay, this is this open interval and c plus delta, this open interval is called your neighborhood of c, right? So here also okay, for all x in some neighborhood of c, but here okay, for all from here to here to here, but not c, is still right. But this condition should be okay satisfied okay. Any value okay near about of c okay, any value, it may be any value, right? Any value of x, but not okay c, right? Except possibly at x is equal to c, except okay, only just in some neighborhood of a c, right? Okay, just here, just let me explain by taking this example. And one, uh, if we have to say, okay, you know, for all x in some neighborhood of c, instead of neighborhood of 1, neighborhood of 1 means okay, just 0.9999, okay, you x okay, maybe these values okay here okay, let's value 1.001 okay, value of x may be this one, but not at x is equal to 1, meaning of this one okay, just neighborhood of 1 means either it may from left hand side or left side of 1, or it may be from right of 1, right? So I think clear this neighborhood of c, except possibly at x is equal to c, and if this limit of this as x tends to c, and the limit of h of x as x tends to c is equal to L, then we can write down without finding the limit of g of x, directly we can say the limit of this must be L. This is the statement of the sandwich theorem, or you can say the squeeze principle. Let me explain. Suppose it is just 1 less than equal to f of x, f of x less than equal to 1, right? If we see the limit of x tends to c as 1 is equal to 1, as we know, right? It doesn't matter okay, 1 is a constant, limit of this one 1, and limit of this function, limit of this one is 1, limit of this also, limit of 1 again x tends to c is equal to 1. So limit of this one, limit of this one is 1, and then we can say therefore by squeeze principle or a sandwich theorem, we can say the limit of f of x as x tends to c is equal to 1. All right, so again let me explain. If we have suppose here f of x less than equal to g of x less than equal to h of x, right? Here if we have a limit of x tends to c, f of x is equal to suppose 2, let's suppose okay 2, and limit of h of x as x tends to c okay is equal to 2, okay, and then by this principle we can say okay, by sandwich or squeeze principle, by sandwich or squeeze principle, limit of gx as x tends to c is equal to 2. I think clear okay, what is the statement of the sandwich theorem, right? This is the statement of the sandwich theorem, okay. All right, so so we can apply while finding the limit of functions, right? Limit of functions. And now here here's some results I have written. Okay, limit of f of x as x tends to c negative. Here I think you are in confusing if you are okay just watching this limit of function first time. Limit of function as x tends to c negative is equal to, we can write down limit of function c plus h as h tends to 0 negative. What is the meaning of this one? This means here negative means negative, or a positive sign means not okay, number is negative or a number is positive, okay, okay. So this doesn't signify this, but it tells your here, okay, value of x approaching, value of x is approaching laptop, see here, right? So here, okay, laptop 0, okay. Here, okay, if we are suppose, okay, a limit of x tends to 1 negative, here instead of f of x we have 2x plus 1. And if we are not comfortable with this and we want to as x tends to 0, and we can write down, okay, and limit h tends to 0 negative, here f of c plus h. What is a c? See here we can write down 2 1 plus h plus 1, we can write down this, right? So we can replace x by c plus h, and here h is tends to as h tends to 0 negative. 0 negative means, okay, h approaches from left top 0 negative, we can write down according to this property, right? Okay, so it's clear. And later I will tell you when we will do the left hand limit and right hand limit. At that time we will discuss again, and you will understand negative and positive sign, right? Negative, here negative, I have told, okay, negative x approaches from left of c, and here h approaches from 0 negative, the left of 0, right? So if we are comfortable with c while finding, and we feel more comfortable as okay h tends to 0, that's why, okay, we can convert, okay, this limit in this form, right? This limit of function is equal to, in this form, is equal to limit of this, right? And here also same case it happens here, it works here also, limit of function as x tends to c positive. Here c positive means your x approaches from right of c, and we can write down same as I discussed, okay. And same case, okay, same case happens, okay, if we have only left limit not discussed and the right limit not mentioned, okay, and then simply limit of function as x tends to c, we can write down the limit of f of c plus h as h tends to 0, okay. So I think clear how to use, I have told you, right? Okay, squeeze principle clear, and these properties are also clear. Hmm. Let's see, this important theorem on limits we need in many places while finding the limit of function. Especially this theorem works if we are going to find out the limit of algebraic functions. All right. So let's see how to prove this theorem. Okay, let's find out important theorem on limits. Say limit of x raised to power n minus a raised to power n x minus a as x tends to a is equal to, let's divide by actual algorithm, by actual division, or algorithm division. Here x raised to power n minus a raised to power n. Here you can learn also how to divide rational expression, oh, here algebraic expression. Here we have x raised to power n minus a raised to power n algebraic expression. Here I have taken. So see, now I'm going to divide by actual division. This is your rational algebraic expression, numerator, and this one is your denominator. So here by actual division I'm going to divide x raised to power n minus a raised to power n by x minus a. So as you know, firstly we need how to divide, okay. Firstly we try to make first term same, x raised, we want to get here x raised to power n. So you have to decide, okay, which term we have to take here. right? So that if we multiply by that term, we should get okay x raised to power n, right? See here, x raised to power n minus 1. If we choose this one, x raised to power minus 1, if we multiply by this one by x raised to power n minus 1, and definitely you are gonna get first term x raised to power n. Alright, this into this by law of indices x raised to power n. If you multiply, and it becomes x raised to power n. As you know, okay, here is a power 1, and n minus 1 plus 1 cancels, simply x raised to power n. You have studied already in law of indices, right? By using the law of indices, if we multiply, we can simplify x raised to power n. And now this into this, simply a raised to power a x raised to power n minus 1. Yeah, just change, okay, we change the sign, okay, as we do in actual division, minus, and this sign becomes, okay, like same terms, okay, x raised to power n minus x raised to power n cancelled, and here these are not like terms, so they cannot be simplified. Here we need to write down simply a x raised to power n minus 1, and we write down as it is, okay, this term minus a raised to power n, okay. So again, try to make same here also, same. So choose firstly plus, yeah, because of the plus sign. So plus sign taken here. Okay. Now if you multiply by a x raised to power n minus 2, then what you will get? Okay, here you will get a x raised to power n minus 2. I think now you understood. And here minus a square x raised to power n minus 2, and change the sign, minus and plus get cancelled, and these two are not like terms. Here a square x and minus 2, again you write down here minus a raised to power n, okay, and plus you need here a square x raised to power n minus 3, then you will get here a square x minus 2 minus a cube x raised to power n minus 3, right? And minus cancel here, plus, okay, you will get here a cube, right, x raised to power n minus 3, and minus a n, right here. Alright, and so on, okay. If we extend this process to n terms, we are going to get, okay, see here, what we'll get, okay. If we extend, okay, up to n terms, let's make the sequence up to n terms, x raised to power n minus 1, you are going to get, and plus a x raised to power n minus 2, plus okay, now I think understood here. Now I'm going to make plus, sorry, here I forgot to write down limit, is equal to limit of as x tends to a. Here I'm writing now quotient, you can say x raised to power n minus 1 plus a x raised to power n minus 2 plus a square x raised to power n minus 3 plus a cube. Similarly, let's see here, a power 0, a1, a2, a3, x raised to power n minus 4, okay, n minus 4, so plus, so on, dot dot, and your final term will be, see, look at here, you can say how to make the final term, how to write down the nth term. Here is power of a is 0, here 1, if we have a second term 1, and if we have third term 2, and if we have nth term, we will have, okay, a n minus 1, you see, and if you a n minus 1 into this and into this last, what you are getting, a raised to power n. So a raised to power n, so it will be cancelled out, right? Finally, when you will extend this process to n terms, and you are going to get 0 as a remainder, a raised to power n, alright, is equal to limit of I'm writing again this x raised to power n minus 1 plus ax n minus 2 plus a square x n minus 3 plus dot 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 here okay, you can say x raised to power 0, you're gonna get okay, right? This one 0, and simply I'm writing here e raised to power n minus 1. All right, as x tends to a, this is a polynomial. As I have told you already, if you have a polynomial, then we can write down, okay, so limit again, I'm recalling, limit of f of x as x tends to c is equal to f of c if f of x is a polynomial, right? A polynomial. So this is a polynomial. We can write down a n minus 1 plus a into a n minus 2 plus a square a n minus 3 plus dot 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 and a raised to power n minus 1. Okay, up to n terms we have written, up to n terms here, a n minus 1. So a n minus 1 plus a n minus 1 and plus so on. By using law of indices here, you can simplify, and plus a raised to power n minus 1. Alright, not here, is equal to, okay, before writing the answers of this one, let me write down. If we have a 10 plus 10 plus 10, what we can write down? 3 times 10 we can write down, right? So no doubt, you have no confusion here. And if you have, okay, suppose 5 plus 5 plus 5 plus 5 plus 5 plus 5 plus 5, okay, right? So how many times I have written? 1, 2, 3, 4, 5, 1, 2, 3, 4, 5, 6, 7. 7 times we have written, okay? Just you can write on the 7 times 5, right? 75 and here 30 and it's gonna be 35. So similarly, using the same strategy here, same method, we can write down, okay, a raised to power n minus 1, a raised to power n minus plus a raised to power n minus 1 plus a raised to power n minus 1 and plus dot 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 plus a raised to power n minus 1. So how many times these terms are coming, right? So you know, right, we have extended up to n terms, right? So here n term, there are how many terms are there? N terms, okay. So if we have a one term, then same we will write. If we have a two terms, okay, same, okay, repeating, and two terms are repeated, and connected by plus sign, we can write 2 times of e raised to power n minus 1. Okay, again, let me write down, if a raised to power n minus 1 plus a raised to power minus 1, 2 times, I have written same thing, we can write down 2 times a raised to power n. If I write, okay, 3 times, then I can write down 3 times of. If I write, okay, same thing n times, then I can write down here n into a raised to power n minus 1. Okay, so this is the limit of this function. We can write down here limit, therefore limit of x raised to power n minus 1 e raised to power n x minus 1 as x tends to a is equal to n a n minus 1. And now this result and this theorem we can apply to find out the limit of algebraic functions, right? In trigonometric functions, okay, we don't use, later I will tell you, we don't get, okay, this type of situation in trigonometric functions. This theorem is a special use in algebraic functions, right? And sometimes, okay, we can use in I think log ax, no, okay, only in algebraic functions, okay, we use generally this theorem, right? So very important theorem while finding the limit of algebraic functions, okay? And remark, okay, this theorem here I have written, okay, n belongs to capital N means set of natural numbers, right? Set of natural numbers, and n is your set of natural numbers, okay? So, and if n is your any natural number, then this theorem is satisfied, right? Here I have proved by using n as a natural number. If so, If n is a positive, if n is a negative integer, simply you can if n is integer, negative integer or natural number or positive integer, same thing. If negative integer, zero integer, or rational numbers, then does it work? Yes, it works. Okay, I've not proved. Okay, I've not shown here, so it's a lengthy process. You understood how to find out and how to if n is set of a natural, n is n belongs to set of natural number, or n is any natural number, then we can divide in this way, right? We can use, okay, actual division. Okay, n belongs to n set of natural number. And yeah, I asked, okay, I raised one question: does it work? Does it work? Okay, if n is negative integer, zero integer, or simply you can say the irrational number, right? Okay, yeah, theorem. Okay, and the above result is true even when n is a rational number. So it works. Okay, if your n is rational number means, okay, n may be positive integer, n may be negative integer, or n may be natural number. By the way, okay, for natural number we have done, all right, although we have, okay, proved, all right. And or any number which is in the form of p upon q, rational number, right? P upon q, okay, rational fraction, p upon q, q is not equal to 0, and p and q are integers in any, okay, rational, this is a rational number, right? P upon q, q is not equal to 0, and p and q both are integers, right? This is called the rational number. N is any rational number, okay? In rational number, in the set of rational number, we might have, okay, positive integer, we might have a negative integer, we might have a zero, all right, or a fraction number also, right? Fraction number means in this form 1 upon 2, 2 upon 3, right? So this theorem works, okay, right? This theorem works for a rational number also. Okay, I think clear how to prove. Now I'm just, okay, going to how to apply this theorem. Here is equal to n e raised to power n minus 1. Now let me take, okay, just if you get, okay, evaluate limit x tends to 2 x raised to power n into 2 raised to power, here x raised to power 3, 2 raised to power 3 upon x minus 2. Okay, exactly, you have to see firstly, okay, whether this form is not, whether this form is in this form or not, right? You have to check firstly, okay. Yes, exactly in this form. This question is similar type of, because here x raised to power nn and nn, here x minus a, x minus a, x minus a, and x tends to a, x tends to a. Okay, all right. So exactly this question is just like this theorem. Now we can write down, okay, by using, okay, this theorem. All right, if you get a key value and solution, we can find out, we can use, okay, we can use like this way, limit of x to cube and x upon x minus 2 as x tends to 2 is equal to, directly we can apply this theorem. According to this theorem, we can write down n 3 into 2 raised to power 3 minus 1. So 3 into 2 raised to power 3 minus 1, 2 into 3 or into 4 is equal to 12. Okay, so here we have since we can write down, since limit of x raised to power n, e raised to power n, x minus a as x tends to a is equal to n minus, sorry, n a raised to power n minus 1, right? So we can use, right, n a n minus 1, 3 into 2 raised to power 2. So 3 into 4 is equal to 12. 12 is the limit of this function. Okay. We will take this type of more these type of questions, right, later. Okay, now see, yeah, clear this how to use this theorem, right, to find out the limit of function. Okay, then problems on, see, I have written here one more line. Okay, problems on the limits can be divided into following two categories. I have written categories: algebraic limits and second is non-algebraic limits. So algebraic limits you understood, I think, okay. And if you are finding, okay, limits of algebraic functions, and it's called the algebraic limits, because problem, these are the problem based on the algebraic limits. And if function is not algebraic, means if you are not going to find out the limits of the algebraic functions, then you might have, okay, then you might be, okay, engaging with trigonometrical function, finding the limit of trigonometrical function. You might have your exponential functions, logarithmic function. These all are, okay, non-algebraic functions, right? Non-algebraic, or you can say the transcendental functions, right? Transcendental function means which are not algebraic function. Trigonometric functions, exponential, logarithmic, hyperbolic function. These are all non-algebraic functions, or you can say the transcendental function. Clear? If you are finding the limits of transcendental function, then you can say these are the problems of non-algebraic limits. You can keep these all problems in non-algebraic limits. And if we have, okay, if we are going to find out the limits of algebraic function, you can say these are the problems of algebraic limits. Okay, so in next video definitely I'm going to evaluate or find the problems of limits of algebraic functions. So we will find out the limits of algebraic functions. And okay, we will have in next video, okay, algebraic limits. And wait and watch, go through all my videos, and don't forget to subscribe. If you subscribe and press bell icon, you will get video immediately as I upload here in your mobile or a laptop, in any other, okay, gadgets where you can get okay. So all right, have a wonderful time. Bye bye.